So, the LightCure project. What is it about? So first of all, I want to show you the logo. We just developed it a couple of weeks ago. In the middle of the logo, wait a second, this is the laser, yeah, is a lizard. Why is there a lizard in the middle of the logo? What has a lizard to do with congenital hyperinsulinism? I hate to say chai because that sounds like tea, actually. It is because what we are using is something that is contained in the saliva of this animal. And this animal is called the Gila monster. Why is it called the Gila monster? Well, because the city of Gila is where it lives in New Mexico, and it's called a monster because once it bites you, it's not going to let go anymore. Why? Because there's a venom. The saliva actually is sort of a venom, and it takes a while until it works. So you have a couple of minutes while it's biting you until you die. Well, you're not going to die, you're too big for it, but smaller animals will. And one compound in the saliva is actually xanthin. And xanthin is something that binds to a certain receptor. That's a molecule on the beta cells, and in healthy people, it induces insulin release. So if you treat CHI, you don't want to actually induce insulin release. But this molecule is so specific for beta cells that if you use this xanthin, which binds to it, that you can actually visualize the beta cells if you label it with a radioactive dye. So, and this is actually what we're doing. In a healthy person, it's a certain hormone that is made actually in the guts. It's called GLP-1. That's actually released after you eat, and then it induces insulin secretion. But it's very unstable. It only has a half-life of 2 minutes in blood. And the xanthin of the Gila monster is perfect because you can't break it, you can cook it, you can do whatever you want, it's not going to break. And this is exactly what we're looking for targeting beta cells. And this is what we're doing. And actually there was a previous project when I actually got to know Julie and a couple of other people, and I was in the family conference in 2015. With this previous project, we wanted already to develop what we are going to develop in the current project. But while we were doing this project, the legislation changed. We found that the compound that we were using didn't do what it should be doing, and this was also new for the company that had developed it, and I'll explain you later what it is. So we were facing a lot of problems we didn't expect, so we didn't reach the final aim that we had then. And this is what we're going to do in the current project. So this project started with improved imaging of insulinoma. Insulinoma are insulin-producing tumors. It's a little bit the same thing as congenital hyperinsulinism, but it's in adults who develop those tumors, and then they have the same symptoms, actually, more or less, as children with CHI. And what you're seeing here is the standard scan that was done. It's a Gotthardt PET scan, that's what it's called. And they're looking for the tumor. And if you look at this scan, it's also a tumor in the pancreas. If you look at this scan, are you seeing the tumor? I mean, this is the liver and the spleen, pancreas somewhere here. There are a lot of hotspots there. What's the tumor? So when you use xanthin and you label it with a radioactive tag, and you take the same scan with xanthin, it's going to look different. Is anybody seeing the tumor? Exactly. So if you're not totally dumb and blind, you cannot miss the tumor. And this is actually what happens in adults. So we saw this and thought, whoa, this is cool, this is working. And this is how such a scan looks like when you do it in clinical practice. You have a CT and a PET scan, and they're sort of combined, and then you're seeing the tumor. It's really popping out. So we thought, whoa, if this is going to work in adults, why shouldn't it also be working in children with CHI? But first of all, before I said something about CHI. This is actually, we ended up in the newspapers when we published the study showing that the Exendin scan was actually superior to the combination of CT, MRI, endoscopic ultrasound, dotted talk PET. If you combine all of them, you still don't see all the tumors that we are seeing with Exendin. So it's really a step forward. So we actually made it to the news and in the newspaper. And what it says is that saliva of the Gila monster helps to find tumors. Very nice title. And this is about somebody who says, I can't breathe when I'm in the city. This is about punishment for a murderer. And this is about a guy who actually told his teacher that he was going to shoot him with a Kalashnikov. And then we're in the middle of that with the saliva of a Gila monster. That's science, okay? And actually, there was an interview of a patient, and I want to tell you the story because this patient had an insulinoma. And he had symptoms, like he was not there. He was sort of, he was not dropping on the ground or something, but he didn't react. He was sort of very strange. And actually, he was diagnosed with a psychiatric disease. So he was treated in psychiatry for 3 years. Until he went to the election, and when he had actually done his work there, he sort of dropped on the ground. And then a paramedic, not a doctor, they've been treating him for psychiatric disease for years, a paramedic checked his blood sugar. And it was something like 1.2 or 0.9, very low. And then he was diagnosed with insulinoma. And then he went to us. He was one of the first patients to participate in the study. We found the tumor, he was operated on, and a couple of weeks later we got this email, the whole team got this email from him, and the title was Long Live Exendin. And that was really great for us. He also gave an interview to another newspaper, national newspaper, which is called The Telegraph. That's about the same thing as in UK, The Sun. So very funny. And then we actually also tried it in children with CHI. And we have a standard that is DOPA PET. And when I'm showing this image here, I show one where DOPA is not as good as Exendin, but it's not as black and white as that. We don't have final proof that Exendin works better than DOPA, but it does have a couple of little advantages. It has a little bit of a higher target to background ratio, so there's less uptake in the normal pancreas in comparison. So we have some preliminary data going in this direction, but we don't know for sure yet. We need some more data to really prove it. But the images look good. So what we're right now doing is we're putting this radioactive tag on the molecule. This is the molecule, the Exendin. It's a polypeptide, so it's lots of amino acids. It's a chain of amino acids. And we put this radioactive tag on it. We inject it into people. We put them in the scanner, and then we get these images that I just showed you. But the thing about it is that Exendin can also be a carrier. So you can put something else on the Exendin and deliver drugs to the beta cells, for example. What we also did, and this is an example from ovarian cancer, so a totally different story. You don't see the cancer when you look at it, but if you have a folate which is labeled with a fluorescent tag, you actually see it shining there when you look at the fluorescent light. And actually we wanted to do the same thing for CHI, because finding the focus when you operate on children with CHI, with a focal CHI, I mean the pancreas is like my thumb, right? It's not bigger than that, and then you have to remove the focus. And if you could see it by fluorescent light, we thought it would be a really step forward. And this was something that we wanted to do in the LightCure project. So we wanted to add this fluorescent tag, which we have done. As I told you, the legislation has changed a little bit. We had a couple of other pharmacological or pharmaceutical problems. And we have the compounds, it's GMP, but we can't inject it in patients because it has some properties that makes it difficult to make the final quality control. So the compound works. We've tried it in animals, in pigs and in mice and in rats. It works. It does exactly what it's supposed to do. But for legal reasons, we cannot inject it in patients because the quality control that we are doing, the way you do it technically, is not working. And there's no way around it, so we can't do it. Frustrating. So we thought we'd take it to the next step. And we said, well, let's do something else. If we don't do it with this fluorescent tag and it doesn't work, we can do something else. We can put, that's a light bulb. It's actually a symbol for a photosensitizer. A photosensitizer is a molecule that you actually find in solar modules, for example. When you activate it with a light of a certain wavelength, it will produce radical oxygen species. And these actually can damage cells. They're toxic. So what we actually want to do, we want to inject this into patients. The compound goes to beta cells. It's highly specific. It's not in the exocrine pancreas. It goes to beta cells. And then it's specifically taken up by the beta cell. So if you have a focal lesion, it's in the focal lesion. But it does nothing. It does nothing. But if you activate it with a laser, it's going to kill the cells. This is what we're trying to do. Does that work? Good question. We actually tried it in mice. So we used nude mice, transplanted this beta cell tumor in those nude mice, and wanted to try whether it works, yes or no. And if you let the tumor grow, they're going to die because they get hypoglycemia, right? And what we actually did is we treated those animals, and what we saw was that those that had the treatment were surviving longer than those that didn't. So it does work. It is super efficient. If you use too much light, you're not going to burn the tumor only, you're burning half of the mouse. It's not a problem in humans, it's a problem in the mice because the concentration is high, it's a very small animal. But it's super effective. And this kind of therapy is also used in cancer treatment right now with antibodies that bind to certain cancers and you activate them. It seems to work very nicely, but nobody's ever tried it in a basically benign disease, in a non-cancerous disease. But what we're aiming for is to treat people with this. And this is actually what the LightCure project is about. So this is the first page of the LightCure project. You see we have 12 partners in there. It's a pretty big project. It's 8 million euros in total. And a couple of people from the project are here. So there's Steffi back there. There's Diva in the scientific advisory board. We have all the people from CHI International. We have Henrik, who's also in the scientific advisory board.
Antonia.
Did I forget anybody?
Antonia.
Oh yeah, Antonia, right. Yeah, Antonia is also in there, sure. So there are a couple of people from the project here.
Oh, yeah.
Sorry?
Oliver.
Oh yeah, but he's not here. They don't see him. I think I would see him if he were there. Yeah, Oliver Blankenstein, who was there yesterday, is also part of the project. And yeah, right, patient, and oh my gosh, I forgot the patient. So Anna is in the patient advisory board. Who else? We have Trudy. Where's Trudy?
Maureen's over there.
Right, and Maureen is there. So lots of people. Right, there's Trudy. Right. So a lot of people were there at the meeting we had beginning of the year. That was a kickoff meeting. First time we had a meeting of the whole consortium, and it's actually the fourth consortium in a row that I'm managing on extended development. It's laborious, and always something goes wrong that you don't expect to go wrong, but I hope we'll manage this time and get where we want to get. So this is the structure of the project actually. So we have several work packages, and I just want to introduce you to the different work packages because we are combining a lot of different things here. So work package 1 is actually focusing on the development of the GMP compound. GMP means good manufacturing practice. Anything that is injected into a patient has to be produced according to certain rules, certain legislation. So it's, 20 years ago you could inject things if you were a doctor, it was your responsibility. Nowadays, it's impossible. Production of such a compound costs you hundreds of thousands of euros. You have to do toxicity studies. It's all required, so we have reserved about 1 million for the production of the compound, the toxicity testing, and all these kind of things. And we've been working on how to work with this compound in the previous project, so I hope we'll get there. And then we have work package 2, and work package 2 is actually focusing on defining. So what we want to do is we want to do a PET scan. We want to use that to predict how much of the photosensitizer exendin is actually going into the patient and into the target. And we want to know how much light do we need to kill the cells. But we want to take it one step further. Oh, 1 minute. Oh, I have to speed up. We want to take it one step further, which is, if we don't kill the beta cells, because if you kill all the beta cells, you'll get diabetic. So the question is, can we reduce the activity of the beta cells to an extent which makes it easier to treat people by medication, if it's diffuse disease, right? So we want to stabilize the blood glucose levels. So we really have to figure out how much of the compound you need, how much light you need to activate it, and what the biological effects will be that you achieve. And we are going to do this in animal models, and then we are going to move to the clinical studies where we will first try it in adults with insulinoma. We'll first remove the insulinoma, do the irradiation, and see whether. So we inject the compound, remove the insulinoma, and when it's outside the body, we check whether the technique works. If it works, we'll do the irradiation, the laser irradiation inside the body, take out the insulinoma, look whether the cells are dead, yes or no, and then the third step will be to do the treatment actually in patients. And every step will be followed by the same step in children with focal disease to start with. And when we know it's safe and it's working, then we're going to take the step to the diffuse disease. And then, so we're also investing, that's work package 5, is burden of disease, disease outcome, and also standardized decision making, because we realized that we don't know what the burden of disease is, of this disease. It's never been scientifically evaluated properly. We have some data about quality of life, but also how are people informed by their doctors? How are decisions taken on whether you operate on people, yes or no? Can we standardize this? Can we help doctors to discuss this with the patients and the families of the patients in a more decent way? Because I think there are really big differences between different centers, how these things are managed, and everybody wants to provide the best care, but not everybody knows how to do it, I guess. And then we have work package 6, which is the co-creation with patients, awareness raising, engaging stakeholders, aiming also to reduce brain damage. And we're investing, like in this work package 5 and 6, we're investing, it's 1.5 million euros that goes into these work packages, because we think that also informing healthcare providers is super important to reduce brain damage. And the latest step is that we have asked for additional money from the EU for another work package where we actually want to improve early diagnosis. So one is that we want to contribute to what Diva is also doing with her consortium to figure out what the glucose metabolism is and all these fatty acid things and whatever. And the other thing is that we have somebody from Portugal who's working with microvesicles. So every cell sheds little vesicles, so that's lipid blobs. And inside this lipid blobs you find things that are from the cell. And these lipid blobs contain genetic information about the proteins that are actually made by the cell. And we want to analyze this genetic information from the blobs to figure out whether it's different. I mean, if you have cancer, you can find it in there. If you have diabetes, you find it in there. So why don't you find it when you have CHI? So the idea is to take a little heel prick, little blood from there, analyze those blobs, and figure out whether we can find a genetic profile that's typical. Well, it's not a genetic profile, it's more like the proteins that are made by beta cells that are specific for CHI as a screening test. If this works and we find a certain pattern that is typical for CHI, it'll take another 10 to 15 years to develop into the decent screening test, but we think it's a possibility to do a screening with a little drop of blood. And this is actually what we want to do in this, I know I'm starting to stop in this project. And this is actually my last slide. Thank you for your attention. I hope you are going to make it for this project. I'm grateful actually for all the support that we had in writing the project and working, and all the patients that are contributing and all the scientists. So I really hope we're getting there. And not like the last time legislation changes and we can't do it. But this time I think we're working on it to get it done. Thank you.